Hey guys, today we were looking at the last problem, problem 25, from the AMC 10B 2025 competition, where we're given a square ABCD with side length 4 and points PQ on AD and CD, respectively, such that AP is 8 over 5 and DQ is 10 over 3. So AP is 8 over 5, DQ is 10 over 3. So that means DP is 12 over 5 and QC is 2 over 3. And so we have that a path starts from P and goes to Q, and then it continues by reflecting across each edge it hits. And we're given that a nice property about reflections is that the incoming angle it makes with the edge here will always equal the outgoing angle that it makes with the edge as well. That's just a nice property of reflections, assuming like a perfect world without friction or any other sort of outside factors. And so we're asked to determine, whether or not it ever hits a corner, and if it does, which corner will it hit first? And so the idea behind these sort of reflection type problems is to sort of change your perspective a little and not view the line as reflecting, but sort of the entire board as reflecting every time it hits an edge. And what I mean by this is, as an example, if you've ever played pool or billiards before, let's say we have like a pool table here. That's bad. Right, let's say we have this pocket here, we have a ball here, we have our cue ball here, and we sort of want to make this bounce shot into this pocket. Well, we don't want to guess where we want to hit along this edge, right? So instead, we can reflect this pocket over the line we want to bounce off of, and then we draw this line, right? And the idea is, if the board did extend all the way out here, we would just hit a straight line into this pocket, right? But because it's not, we can make use of the fact that these two angles are the same because they're vertical angles. But then because this pocket is a reflection of our original pocket, we have that this line here will also have the same angle, if we sort of reflect it back now. And so now because we have that, these two blue angles are now the same, because I guess this blue angle is equal to this blue angle, and that blue angle is, and I guess if we mark it green now, this green angle is the same as this green angle. So we have that these three angles are all the same. So we indeed have that this line here is a true reflection. And so if we just aim it at this intersection point that we made, assuming again no friction and air resistance or any other factors, if we aim the cue ball such that it'll hit this ball, or if we aim the cue ball to hit our ball to go this way, it will indeed, hit this intersection point and then bounce off towards this pocket. So that's the idea in pool or billiards, and we can use the similar idea here, right? Where, again, instead of reflecting the line every time it hits an edge, we reflect the board every single time. So let me try to get a copy of this board. We have a board here. Let me white this out. thing. So what I mean now is, right, instead of, looking at the line as bouncing off this way, if we flip the board around across the line DC, so this is our new A, this is our new B, then if we extend PQ out, right, we have that these two angles are the same because they're vertical angles, but we have the property that reflections have to have the same angle, right? So these three angles are all the same. And so we have that, this new blue segment will be exactly the same as as a reflected part after the first bounce, just in this new reflected board. And we can continue this process, right? Now, because the next bounce will hit side BC, we can reflect over that side. So this is our new A, this is our new D. And so our reflection will sort of look like, or if we continue the line, it'll be this way, but the reflection will be in this direction. But again, we have that, this incoming angle will be the same as this reflected angle because they're vertical angles, but reflections maintain the property again that these angles are the same, or the outgoing angle is also the same. So now we have that the new green line in this third sort of grid will be exactly the same as the green line in the previous grid. And if we want to relate it to the first grid, right, this green line will be sort of like this. Right, so you see that, every bounce, if we make a reflection instead, our entire path is now just one straight line, right? And that's so much easier to sort of analyze. And so now if you imagine, right, our path, not that it's a line, if it's just a line traveling through a plane, what does it mean for it to, hit one of these corners? Um, well, if you imagine it's just like a coordinate grid, right? Something like this. A line, what it means to hit a corner, right? If each one of these grids is a board, what it means to hit a corner is to, it has to hit exactly at a lattice point, right? So that's, in this case, it would be 1, 2, 3, 4, 3, right? For it to hit a corner means it has to intersect at exactly a lattice point. But that's exactly what we have here, right? We want to find the first lattice point that this line will intersect. Like, so the only issue is that right now our side length is 4, right? But we can just scale everything down by 4 to get exactly our sort of coordinate grid analogy here. So if you scale everything down by 4, the square will have side length of 1, and we have PQ here. This will be 2 over 5 now, and this will be 3 over 5. And then scaling by 4, we have that this will be 5 over 6, and this will be 1 over 6, I think. Yeah. We have A, B, C, D, P, and Q. Alright, so now that we have the idea that we can actually just view our entire path as one line and find the first lattice point that it intersects. We can now just find a formula for this line, right, and then try to solve it for integer solutions. In particular, we have that y is equal to the slope, which is rise, or 3 over 5, over run, which is 5 over 6. So this is just 18 over 25. So we have y is equal to 25x plus b, or the y-intercept, which is right here, right? I guess we're making a 0, 0. So our y-intercept is just at 2 over 5. And so again, finding the first corner that the line will eventually meet at is the same as finding the first lattice point that this line will intercept at. So we just want to find any positive integer solutions to this. And so, as we don't like fractions, so let's multiply by 25y, let's multiply by 25, so that 25y is equal to 18x plus 10. And so I guess just making all the variables on one side. 25y minus 18x is equal to 10. And so now, how do we find integer solutions to this equation? Well, note that 25 and 10 are both multiples of 5, and 18 is not a multiple of 5. So for any integer solution to be true, we must have that x is a multiple of 5, right? And so we can now just try different multiples of 5. Right? If x is 0, we have 25y is equal to 10, which doesn't have any solutions. If x is 5, we have 25y minus 90 is equal to 10, or 25y is equal to 100. So I have y is equal to 4. So we see that 5, 4 is our first integer, our first positive integer solution. So if we sort of draw it out now, 1, 2, 3, 4, 5. 1, 2, 3, 4. I should draw it out like this instead. This is our 0. 1, 2, 3. That's too big. 1, 2, 3, 4, 5. 1, 2, 3, 4. This point here is 5, 4. And our line will look something like this. And so if this is our first lattice point we hit, well, which corner does this now correspond to, right? Well, in this first sort of grid here, we have this is A, this is B, this is C, this is D. And so we can just go like in this upwards direction now, right? If we reflect the board over CD, we have this is AB. And reflecting the board over AB, I guess looking at this board and reflecting over AB gives that this is CD, and then this board reflected over CD is just, this means that these two are AB. Then we can just go in this direction now. This board reflected over this edge means that this is AC, this is BD, right? We just keep reflecting. This is AC, and this is BD. So we have that the corner here, 5, 4, corresponds to corner B. And so, therefore, the first corner we hit is B. and that's our answer. Yeah, I don't know. I usually like these types of reflection problems because I don't know, the idea of reflecting the board instead of reflecting the line. Uh, I don't know. I find it quite fun to think about. But yeah, that's it for that problem.